Hi, everyone. So today I wanted to give you a brief introduction to ligand field theory and in particular how you can envision metal ligand bonding with sigma only interactions in the octahedral point group. So the problem starts by thinking about the fact that along the X, Y, and Z axes, you have the sigma interactions between the metal and the ligand. And remember, the ligand is donating, or each of the ligands are donating the electron pairs to the metal that are actually making those sigma bonds in the first place. So if you simply use those six sigma bonding vectors as a basis for a representation in the octahedral point group, you will see that you generate now the sigma bonding representation. And if you work your way through all of the operations, effectively wherever those vectors are unshifted are sort of seen in this representation. And then of course you have to reduce that to its irreducible components, and you get the symmetries for the sigma bonding vectors for those ligands. And so therefore the ligand group orbital then becomes A1G plus T1U plus EG. And remember, you started off with E being 6, and remember, you basically have singly degenerate, triply degenerate, doubly degenerate. So if you add all of those up, you will see that you wind up with 6. So that is telling you you've gotten to the correct number of EREPs that were necessary for this problem. So now what do we do with that information? So much like we did with molecular orbital theory, let's now move on and see what metal-based atomic orbitals those ligand group orbitals match up with in terms of symmetry and energy. And effectively, if you do it simply by inspection, you can tell right now that the metal p orbitals are going to be T1U. The metal d orbitals are either T2G or EG. And then the only remaining parts are going to be the s orbitals. And we know that, the metal s orbitals will, of course, always be A1G. So let's now think about that. So here's our representation. And then what else do we really know? Well, I just repeated all of the sigma symmetries that you're going to find above in terms of the atomic orbitals on the metal. And then the one thing that I do want you to take note of is that notice that the dxy, dxz, and dyz are effectively T2G symmetry, which does not have a match. So what you're going to find is those are actually going to be non-bonding in the sigma only bonding scheme in terms of ligand field theory. So then you kind of get to this part of the problem where you realize that if you basically have, representation here that totals 6 molecular orbitals, and then we have symmetry matches on 6 other molecular orbitals or 6 atomic orbitals from the metal center, you're going to get 6 bonding interactions, 6 anti-bonding interactions, and then of course from the T2G set, which are the pi orbitals, those are going to now be 3 non-bonding. So in essence, you can expect that you're going to get 15 MOs in this picture when you draw the diagram. So let's now just take a quick look. And if you do projection operators, which I'm not going to require you to do at this point, and you apply that to the ligand group orbitals, wherever you see the ligand sigma orbital, so that's what the A1G looks like. That's the triply degenerate T1U. So you can see the PX, PY, and PZ symmetries very easily there. And then predominantly you see that you get Z squared or interactions along Z, and then interactions along X squared minus Y squared. And then, of course, the rest of those T2G sets are not going to be bonding. So really what you're going to get from this, again, is now just remember that the d orbitals are going to be the lowest in energy because their value of n is one integer lower than the corresponding s and p orbitals. So in essence, the d orbital or the d atomic orbital energies are the lowest in energy. The corresponding s orbitals are slightly higher in energy, and then the p orbitals are going to be higher in energy with respect to that. But again, you get the idea that with all of these combinations, you're going to get bonding and anti-bonding combinations in each of these instances. And if you just simply add them up, it's like we did by inspection on the previous slide, is that all of these are non-bonding. All of these other interactions where I have plus and minus signs are telling you, you basically are taking in phase and out of phase combinations with all of those symmetry matched atomic orbitals in the metal and the ligand group orbitals that represent all of the sigma interactions. So in the end, you're going to get the same MO picture I told you about, because if you see it, there's 1, 2, 3, 4, 5, 6 of those. So there's going to be 12, interactions. 6 are bonding, 6 are anti-bonding, and then over here you get 3 non-bonding for, again, total of 15 MOs. So let's now take a look at the picture. So now remember, when you're drawing these out, you start with the d orbitals as atomic orbitals with no Ligand field. They're totally degenerate, so that's why these are drawn this way. They're intended to be totally degenerate. And then if these were, for example, the 3D orbitals, this would be the 4s, those would be the 4p. But we sort of know, again, the symmetries of all of these atomic orbitals are really obvious because we have the octahedral character table to work from. And then if you remember, the ligand group orbitals now are just listed here as an entire group. And I don't want to draw over it too much, but they're listed there as the entire group. But you can see very clearly there's T1U here, and then you've got that matches the 4Ps over here. So that's 3 of the T1Us. Obviously, the AG matches up with the 4s atomic orbitals. And then the interesting part is see how the EG only matches up with the EGs here. So what do you start this with? Well, just walk the T2Gs straight across because there's no corresponding group orbital on the right side of the diagram. So then those just march right over and are non-bonding. So that's an interesting thing to see, is that the T2G orbital set in this are completely non-bonding. And then if you look at the EG with the EG, so the green with the green, notice what happens. You make the bonding combination and the anti-bonding combination. The bonding combination obviously is the ligand donating the electron pairs to make those bonds, but then look what happens. Formally now, the EG orbitals that are effectively associated with the d atomic orbitals are actually anti-bonding with respect to the metal ligand bonds. So that's really interesting, the way that that plays out. And then everything else, in essence, is exactly what you would expect. The AG interaction with the AG interaction gives you bonding down here, anti-bonding up here. And then the T1 as we already said, bonding here, anti-bonding here. But the key thing is just recognizing the fact that the EG star, which is associated with the d orbitals now, is an anti-bonding orbital. Now, what do you get from this? Well, now you can see what happens with transition metal complexes. Whatever number of d orbital electrons you have, those literally are going to just fill in this region, and basically they're non-bonding in one case and anti-bonding in the other. So that's an interesting consequence to sort of how the sigma-only interaction picture looks. So let me just kind of summarize this here, is if you have effectively non-bonding d electrons, those are effectively associated exclusively with the metal center. And then, of course, the anti-bonding combination is also really exclusively associated, almost exclusively associated with has the d orbital character. So if you fill these d orbitals with electrons, you'll actually have the ability to break metal ligand bonds, which is pretty interesting. And then, of course, down here, if you think about what happens, you've got 6 pairs of electrons. that's basically 12 sigma bonding electrons, but that effectively gives you a bond order of 6. So there's basically 6 sigma metal ligand bonds that result from that. And that's why that's written in this particular way, is that you're going to get those metal ligand bonds to generate effectively a bond order of 6. Okay, to summarize the complete ML6 sigma-only bonding picture, let's just come up with a few summary statements as to simply describe everything that we've already covered. So the 6 metal atomic orbitals of proper symmetry combined with the 6 ligand group orbitals. And then, of course, the 6 MOs are going to be filled by the ligand electron bonding pairs. So those are all in the box down here at the bottom. And of course, the metal only T2G atomic orbitals are non-bonding. That's why they just walk right over in the MO diagram in this picture. And then the 6 anti-bonding orbitals that are formed as the complementary pair to those are all located up here. And the most important part of that is that the EG star orbital is the lowest energy anti-bonding orbital, and it's anti-bonding with respect to the metal ligand sigma bonds. And as you fill those, you can start to imagine in the octahedral geometry, as you're filling EG star with d electrons, you can start to rationalize why some electron configurations don't really favor octahedral structures, and the structures would rather distort to a different geometry or a lower order point group in order to accommodate the number of electrons that are available. So as you can tell from this, there's a lot of consequences to the observations experimentally that you're going to observe in these pictures. The other part of this, of course, is that the actual magnitude of del O in this particular case is really can be measured optically and with magnetic properties, because those are really representing the HOMO and LUMO of the molecule. So the HOMO are non-bonding base d orbitals, and then the LUMO effectively is the EG star orbitals. So that really summarizes that entire picture. And then the magnitude of del O is going to basically be relevant with respect to the energies of the d orbitals on the metal and the ligand-based group orbital. So really the ionization potentials of the ligand group orbitals tells you where they're going to be located in energy with respect to the d orbitals on the metal. And the point of that being, the closer they are in energy, the more deflection you'll get this direction, and then the more deflection you'll get going up in energy for the anti-bonding orbitals, and then that directly influences the magnitude of del O. And I will continue this discussion in the next presentation. Thank you.